Hello there. Welcome back to Midnight Ocean. I'm Velen, your guide to traveling through the wonders of the ocean. Tonight, we're going to explore each one of the 5 oceans of our planet. If these cozy moments calm you, I invite you to subscribe, share a comment, or leave a like. Now, get comfortable, take a deep breath. Don't be afraid, you're safe here. Let's dive deep into the sea and let our imagination guide us to a peaceful and deep night. The oceans cover about 71% of Earth's surface and hold 97% of all the water found on the planet. In practice, what we call 5 oceans is actually one single continuous body of salt water. No walls, no real physical barriers between them, just conventions established by geographers and oceanographers over the centuries. Technically, the planet has only one ocean, massive, which scientists call the world ocean. And since it's necessary to locate different parts of this same ocean in distinct places around the globe, it became necessary to define boundaries between those sections. Although the ocean is a single body of water, the most widely used division follows geographic, socio-historical, cultural, and scientific criteria that recognize 5 basins: the Arctic, Atlantic, Indian, Pacific, and Southern. The Southern Ocean was recognized by National Geographic in 2021 after decades of debate. Since 1915, when the institution began producing world maps, only 4 oceans were recognized. The 5 oceans together have an average depth of 3,688 meters. If all the land on the planet were pushed underwater, Earth would be a smooth sphere covered by a continuous layer of water more than 2,600 meters deep. Not a single inch of coastline, island, or continent in sight. Picture a border that can't be seen, stepped on, or touched, a purely intellectual line drawn over identical water on both sides. That's how the boundaries between oceans work. There are no underwater walls separating the Atlantic from the Indian, no crystal barriers dividing the Pacific from the Arctic. Despite this geopolitical division, the ocean is one and continuous, hosting different environments and ecosystems and connecting all regions of the globe. What geographers did over the centuries was identify sections of water with distinct characteristics, temperature, salinity, current patterns, and name each one to make navigation, scientific study, and communication between nations easier. With the development of oceanography, the science that specifically studies the oceans, it became clear that there are scientific reasons behind the divisions. Differences in the underwater landscape, temperature, salinity, sediment type, and even the color of the water, which varies with latitude. Think of a big city divided into neighborhoods. The neighborhoods don't exist as standalone physical structures, but each one has its own character. Different architecture, a different feel to the temperature, a different flow of people. The oceans work in a similar way. Each name corresponds to a set of measurable properties that set that body of water apart from its neighbors, even though the water itself circulates freely among all of them. Beyond the physical factors, ocean divisions make navigation and the establishment of maritime routes easier. 3 oceans have been recognized since ancient times: the Atlantic, the Indian, and the Pacific, discovered in the 16th century. The Arctic was incorporated into modern classifications as polar expeditions mapped its frozen waters. The Southern Ocean, though recognized by sailors long ago, had its formal existence constantly disputed. The International Hydrographic Organization went as far as defining it in 1937 and then revoked the designation in 1953, given the strong controversy. Naming oceans, therefore, was never a purely scientific task. It involves international agreements, political interests, and cultural conventions that take decades to solidify. The Southern Ocean also has a particular distinction compared to the others. While the remaining oceans are generally defined by the continents that surround them, It's the Southern Ocean that defines its sister continent, encircling it completely. This reversal of logic reveals something deep about how human beings build geographic categories. Normally, land defines water. We say the Atlantic lies between Europe and the Americas. At the far south, water is so dominant that it's the one that defines where the ice continent begins and ends. What makes the Southern Ocean unique is that it contains the Antarctic Circumpolar Current, the only current that completely circles the globe, which isolates Antarctica from the influence of the outside world, preventing warm air masses from reaching the frozen continent. This current is believed to have formed roughly 34 million years ago. Imagine a river running in a circle around an entire continent, never stopping, never emptying anywhere. That ocean river is what keeps Antarctica permanently frozen and shelters unique ecosystems, completely unlike anything found elsewhere on the planet. The smallest of the 5 oceans is the Arctic, at about 13 million square kilometers, located at the far north of the planet and surrounding the northern regions of Europe, Asia, and North America. Its waters tend to be icy and concentrated within the Arctic Circle. Being the smallest doesn't mean being irrelevant. The Arctic regulates temperature and atmospheric circulation in the Northern Hemisphere in ways that directly affect European winters, Asian monsoons, and the formation of storms in the North Atlantic. A small ocean at the top of the world acts as a thermostat for the entire hemisphere. The Atlantic covers approximately 90 million square kilometers and can be considered the most historically and economically important ocean. During the Age of Exploration, it was the primary route opened up by Europeans. Today, since it borders the most industrialized continents, it's a major route for exports and imports. Its mid-Atlantic ridge, the longest mountain range on the planet, fully submerged, splits it into 2 symmetrical basins and pushes tectonic plates apart from each other, widening the ocean a few centimeters every year. The Atlantic is literally growing while the Pacific shrinks. The Indian Ocean, the 3rd largest at about 70 million square kilometers, is the only ocean that is asymmetrical in terms of seasonal currents. Its surface flows completely reverse direction twice a year, driven by monsoons that determine rainy seasons for more than 1 billion people across Asia and East Africa. No other ocean alternates its behavior with this kind of regularity. It's as if the Indian Ocean breathes, inhaling toward Asia in the austral summer, exhaling back toward Africa in the winter. The 5 oceans together, Atlantic, Pacific, Indian, Southern, and Arctic, cover more than 70% of Earth's surface. This near-total coverage is no geological accident. It's a direct consequence of the amount of water on the planet and the way the continents are distributed across Earth's crust. Naming this single system with 5 different names was humanity's solution to making sense of something too vast to be treated as one thing. The same ocean that swallowed Magellan's ships, that carries cargo containers today, and that will determine the fate of coastal cities as its level continues to rise. The Pacific Ocean is the largest and deepest of Earth's 5 oceans, covering more area than all of the planet's land combined. It has a surface area of 165 million square kilometers, about 30% of the planet's total surface, and an average depth of 4,280 meters, with the deepest point in the Mariana Trench at 10,911 meters. The Pacific Ring of Fire stretches roughly 40,000 kilometers in a horseshoe shape and contains the majority of Earth's active volcanoes, around 75%, and nearly 90% of its largest earthquakes. The maximum east-west width of the Pacific is 19,300 kilometers, enough to cross nearly half the planet in a single stretch. Ferdinand Magellan called it the Pacific Sea in 1521, after crossing the rough waters of the strait at the southern tip of South America and finding calm winds on the other side. Putting 165 million square kilometers into perspective requires a concrete comparison. All of the planet's land surface, every continent, every island, every mountain and desert, adds up to roughly 149 million square kilometers. The Pacific is bigger than that. By itself, if you could stack all the continents inside this ocean, there'd still be leftover space equivalent to the entire area of South America. No other body of water or land on the planet comes close to that scale. The Pacific isn't just the largest ocean. It's the single largest geographic feature on Earth's surface, period. The name Pacific was given by the navigator Ferdinand Magellan in 1521 when he crossed these relatively calm waters during his circumnavigation. The peacefulness suggested by the name, however, contrasts sharply with reality. The Pacific is the stage for intense natural phenomena, including earthquakes, tsunamis, and volcanic eruptions due to the famous Ring of Fire. Magellan got lucky. He crossed the Pacific during a window of calm between storms and didn't live to see the contradiction embedded in the name he left behind. The ocean he called Pacific produces the most destructive geophysical events on the planet with unsettling regularity. The Pacific Basin is nicknamed the Ring of Fire because of the seismic and volcanic activity along its edges. The resulting chain of volcanoes stretches about 37,000 kilometers and comes to life where the Pacific tectonic plates slide against or collide with neighboring plates. Subduction, the phenomenon where one plate dives beneath another, contributes to the formation of extremely deep trenches. Picture a giant horseshoe wrapping around the largest ocean in the world. Every point on that horseshoe is a boundary between tectonic plates in permanent collision, building up pressure that gets released as earthquakes and eruptions. The Earth in that region is literally in a state of geological boiling. The Mariana Trench is the deepest location in the oceans, reaching a depth of nearly 11,000 meters. It's located in the Pacific Ocean, east of the Mariana Islands, at the convergent boundary between the Pacific and Philippine tectonic plates. To put that depth in perspective, Mount Everest, at 8,849 meters, could fit entirely inside the Mariana Trench and would still be submerged under more than 2 kilometers of water above its peak. The pressure at the bottom of that trench equals more than 1,000 atmospheres, enough to crush conventional submarines like empty cans. The Valdivia earthquake in Chile, which occurred in 1960, is the strongest ever recorded in history at a magnitude of 9.5, and it happened exactly at a subduction zone in the Ring of Fire, where the Nazca Plate dives beneath the South American plate. That event released more energy than all the earthquakes recorded throughout the rest of the 20th century combined. The tsunami it generated traveled across the entire Pacific, reaching Japan and the coasts of Hawaii hours later. A single geological event at a Pacific Plate boundary temporarily reshaped the coastlines of half the planet. The Pacific's east-west width of 19,300 kilometers means that a plane flying at a typical cruising speed, around 900 kilometers per hour, would take more than 21 hours to cross it in a straight line. No flight route operates that way, precisely because the distance is impractical without stopovers. For 16th century sailors, crossing that stretch meant months at sea without sighting land, without resupply, with constant risk of scurvy and storms. Magellan survived the crossing. Most of his crew did not complete the return voyage. The Pacific Ocean has a total area of 180 million square kilometers. The difference from the 165 million includes marginal seas and an average depth of 4,000 meters. It accounts for about 1/3 of the planet's total surface. That single third contains more water than all the other oceans combined. It also contains the majority of the world's oceanic islands, estimated at more than 25,000 islands, including those of Polynesia, Melanesia, and Micronesia. Entire peoples who developed seafaring cultures thousands of years before any European even imagined that ocean existed. The average depth of more than 4,000 meters means that most of the Pacific is completely dark. Below 200 meters, sunlight does not penetrate in any meaningful way. Between 200 and 1,000 meters, there is only enough twilight for visual perception, but not for photosynthesis. Below 1,000 meters, absolute darkness and increasing pressure create an environment that scientists long imagined to be sterile. Research in the Mariana Trench proved the existence of abundant life even at the greatest depths, sustained by chemosynthesis, chemical energy released by underwater volcanoes, with no dependence on sunlight whatsoever. The size of the Pacific has direct consequences for humanity that go well beyond geography. This ocean contains roughly half of the planet's oceanic water. Its capacity to absorb and redistribute heat is so enormous that small variations in its surface temperature can reorganize the climate of entire continents. The Ring of Fire influences regional ocean climate. The active volcanoes in the Pacific off the west coast of the Americas, combined with other factors, warm the waters near Peru, triggering cyclical climate anomalies, among them El Niño and La Niña. The world's largest ocean is also the planet's largest climate engine. The Pacific doesn't just take up space, it generates climate. During an El Niño event, surface waters in the central and eastern tropical Pacific become significantly warmer than usual. The trade winds that blow from the Americas toward Asia weaken and can even reverse, allowing large masses of warm water to shift from the western Pacific toward the Americas. The effect doesn't stay in the Pacific. A strong El Niño alters patterns of rain and drought across every continent, causing droughts in Brazil, flooding in Peru, wildfires in Australia, and unusual snowstorms in the United States. As of 2026, 5 major El Niño events have been recorded in history. Pacific water warmed at one point along the equator can reorganize the rainfall patterns of populations that have never even laid eyes on the ocean. Under normal conditions, the trade winds blow from the oceans toward the central Pacific along the equatorial region, generally moving from east to west and pushing surface waters in the same direction. As those waters shift westward, they're replaced by cooler water rising to the surface, a process known as upwelling. Imagine a continuous oceanic conveyor belt running along the equator. Warm water leaves the Americas heading toward Asia. Cold water rises from the depths to fill the gap. This mechanism regulates temperature, nutrients, and precipitation across thousands of kilometers. During El Niño, that balance weakens. Surface waters in the central and eastern Pacific begin warming above average. This warming alters global atmospheric circulation and reshuffles climate patterns across different continents. That's why a phenomenon localized in the Pacific can affect everything from rainfall patterns in Brazil to hurricanes in the Atlantic, droughts in Africa, temperatures in Europe, Asian monsoons, and wildfires in Australia. The conveyor belt has stopped, or reversed. Warm water that should be on the Asian side of the ocean piles up on the American side. That redistribution of heat is enough to throw off the entire planetary atmospheric circulation. The physical mechanism behind this involves something called the Walker circulation, a giant cell of atmospheric convection linking the western and eastern Pacific. Under normal conditions, moist air rises over the warm western Pacific, producing heavy rainfall in Indonesia and Australia, then descends dry over the eastern Pacific, keeping Peru arid. This atmospheric current is a crucial part of the circulation system that occurs in the tropical Pacific, and its ability to influence climate lies in the direct interaction between ocean and atmosphere. When El Niño weakens this circulation, Indonesia dries out while Peru floods, a complete reversal of the usual pattern. The most intense El Niño episodes have left deep marks on the global economy and climate. The 1997 event triggered severe droughts, historic flooding, infrastructure destruction, and agricultural losses across different continents. The 1997 to 1998 El Niño was the most powerful ever recorded instrumentally up to that point. Conservative estimates put global economic losses in the tens of billions of dollars. Regions that depend on dryland farming, without irrigation, relying solely on rainfall, suffered devastating crop failures. Populations that had never heard of the Pacific or the Walker Circulation went hungry because of water temperature in a distant ocean. The consequences of El Niño are global and include an increase in average temperatures on a planetary scale, shifts in rainfall and drought patterns, intensification or reduction in hurricane frequency depending on the region, and damage to agriculture, water supply, and food security. Each of these effects has its own chain of consequences. More intense hurricanes in the eastern Pacific and fewer in the Atlantic is not symmetry, it's reorganization. Some regions take on more destruction, others get temporarily shielded. The apparent randomness hides a strict physical pattern. The phenomenon doesn't happen on its own. El Niño is part of a broader system called YENESO, El Niño Southern Oscillation, which involves complex interactions between ocean and atmosphere. Its cold phase, La Niña, has the opposite effect. The equatorial Pacific records temperatures below the historical average, strengthening the trade winds and deepening normal climate patterns instead of reversing them. La Niña is not simply the absence of El Niño. It's its active opposite, generating equally significant effects. Drought in Peru where El Niño brought flooding. Rain in Australia where El Niño brought drought. The Pacific swings between these extremes like a climate pendulum. El Niño generally occurs at irregular intervals, every 2 to 7 years, and can last from several months to over a year. That irregularity is what makes forecasting so difficult. There's no reliable calendar, no guarantee that the next episode will come in 2 years or in 7. Modern computer models can anticipate events months in advance, which allows for warnings and preparation. But the reliable forecast window is still too short for multi-year agricultural planning, which is exactly what vulnerable populations would need. The heat stored in the oceans functions like a planetary thermal battery. The Pacific, being the largest, stores the greatest share of that energy. When the ocean releases accumulated heat during an El Niño, it's essentially returning to the atmosphere's solar energy stored over the previous months or years. The Pacific Ocean, warmed at one point along the equator, can reorganize the rainfall patterns of populations on continents that have never had any visual contact with that ocean. Farmers in the Brazilian Sertão, herders on the African savanna, and agricultural workers across South Asia are all, without knowing it, dependent on the behavior of a strip of equatorial water in the largest ocean on the planet. YENESO is considered the dominant mode of interannual climate variability on the planet, one of the most important natural mechanisms through which ocean and atmosphere exchange energy and reorganize global climate from one year to the next. In plain terms, of all the natural factors that make a given year drier or wetter than the last in any part of the world, YENESO is the most powerful and most far-reaching. Other factors exist, volcanic eruptions, solar variations, but none simultaneously reorganizes the climate of so many continents with the cyclical regularity of the equatorial Pacific. The ocean that Magellan called Pacific in 1521, because he happened to find, at that specific moment, calm winds, is, in reality, the most active and influential system on the planet in climate terms. A strong El Niño alters rainfall and drought patterns across every continent, causing droughts in Brazil, flooding in Peru, wildfires in Australia, and unusual snowstorms in the United States. From the surface, it looks like water. From the perspective of atmospheric physics, it's the engine that drives the climate of half the planet, and whose behavior, as global temperatures rise, becomes increasingly difficult to predict with the precision that billions of people would need in order to adequately prepare. The Atlantic covers 106 million square kilometers, the second largest ocean, and has a feature that no other ocean has to the same degree: the Atlantic Meridional Overturning Circulation, known by the acronym AMOC. The AMOC carries warm water northward toward the poles along the surface and cold, dense water southward in the depths, also circulating nutrients along the way. It is the Atlantic component of thermohaline circulation and plays a substantial role in regulating heat near Earth's surface. The Gulf Stream, part of the AMOC, transports roughly 30 billion kilograms of water per second along the east coast of North America. This warm current carries water that can be 5 degrees Celsius to 15 degrees Celsius warmer than the surrounding waters. Without this mechanism, northwestern Europe would be several degrees colder. Mathematical models suggest the AMOC has been gradually weakening since the late 19th century. Imagine an ocean conveyor belt with 2 levels. On the upper level, the surface, warm water from the tropics travels northward toward Europe and the Arctic. On the lower level, the depths, that same water, now cold and dense after releasing its heat, slowly returns southward toward Antarctica. This system transports warm surface waters to the North Atlantic and the cold, dense waters back south. In the south, near the tropics, the ocean water is warmer, and the AMOC carries it northward, along the surface, toward regions where it's very cold. This conveyor belt has been running for thousands of years, without an electric motor, without a pump, driven purely by the difference in temperature and salinity between adjacent water masses. The AMOC transports up to 25% of the total heat flowing toward the northern hemisphere and plays a fundamental role in the climate of northwestern Europe. The Atlantic Ocean is the only ocean where the heat flow runs predominantly northward. This singular asymmetry explains why London, located at the same latitude as severely cold parts of Canada, has relatively mild winters. It's not latitude that keeps Europe warm. It's the ocean. The current carries thermal energy accumulated in the tropics and gradually deposits it along European coastlines, like a giant radiator fed by equatorial heat. According to researcher Maya Benyami of the Technical University of Munich, the AMOC raises average temperatures in Norway by about 10 to 15 degrees Celsius. Without it, winters would be far more brutal in those areas. 10 to 15 degrees Celsius of difference is no minor detail. It's the difference between a cold winter and a city that becomes uninhabitable for months. It's the same range that separates a pleasant spring from an agriculturally destructive frost. The AMOC doesn't just make Northern Europe more comfortable. It determines what can be grown, where populations can thrive, and how urban infrastructure has been built over centuries. The mechanism that drives this conveyor belt depends on a delicate balance between temperature and salinity. Salt water is denser than fresh water. Cold water is denser than warm water. When the warm, salty current reaches the North Atlantic, it loses heat to the atmosphere, and that drop in temperature, combined with high salinity, causes the water to sink. As massive amounts of fresh water from Greenland's melting ice enter the ocean, the salinity of surface waters decreases, a process that can create a feedback loop contributing to the weakening of the AMOC. Fresh water from melting ice diluting the salinity is water that doesn't sink, and water that doesn't sink doesn't return southward, weakening the entire conveyor belt. Recent studies show that the AMOC is in its most fragile state in over 1,600 years, a weakening associated with rising global temperatures and changes in the composition of ocean waters. Researchers have identified that the system is already showing signs of approaching a tipping point, which could lead to abrupt and irreversible changes. 1,600 years of data reconstructed from ocean sediments, tree rings, and corals represent a long enough historical perspective to reveal trends invisible within just decades of direct observation. The signal is clear: the conveyor belt is losing strength. Around 2021, the IPCC's sixth assessment report stated it was very likely that the AMOC would decline within the 21st century, and that there was high confidence that the changes would be reversible within centuries if warming were reversed. Reversible within centuries is a phrase that deserves careful reading. It means that even with the complete reversal of the conditions causing the weakening, the ocean would take generations to recover its current state. Ocean systems don't respond to the world on a human timescale, they respond on a geological one. Global warming could, through the weakening of thermohaline circulation, trigger cooling in the North Atlantic, Europe, and North America. This would particularly affect the British Isles, France, and the Nordic countries, which are warmed by the North Atlantic drift. The main consequences also include increased flooding and storms, collapse of plankton stocks, and shifts in tropical rainfall patterns. The paradox is total: global warming causing regional cooling. Europe could face harsher winters precisely as a consequence of a warmer planet, because the conveyor belt that kept it warm would lose strength while the rest of the world accumulates heat. Thermohaline circulation doesn't only affect Europe. It connects all the oceans in a single global conveyor belt that takes roughly 1,000 years to complete one full cycle. Nutrients, dissolved carbon, and oxygen travel through this system, redistributing resources to the ocean depths that sustain entire food chains. The AMOC is part of the planet's largest conveyor belt, thermohaline circulation, which moves water from one side of the oceans to the other, carrying heat from warm regions to colder ones. Weakening this system isn't just a regional climate problem. It's altering the metabolism of the planetary ocean. The current that warms Europe crosses the Atlantic without a passport, without borders, indifferent to human political divisions. Much of the heat transfer in the Atlantic occurs because of the Gulf Stream, a surface current that carries warm water from the Caribbean northward. Although the Gulf Stream as a whole is driven by winds, its northernmost segment, the North Atlantic Current, draws much of its heat from thermohaline exchange in the AMOC. Two distinct forces, wind and density, work together to keep the ocean heater running. Remove either one beyond a certain threshold, and the system reconfigures itself into a different state, with consequences that European populations would take generations to fully absorb. For centuries, the Atlantic was the main navigation corridor between Europe, the Americas, and Africa. Today it remains the ocean with the highest density of maritime shipping routes on the planet. Most of Earth's hurricanes form over the Atlantic Ocean. Its area is about 106 million square kilometers, and it covers roughly 20% of Earth's surface. It contains about 29% of Earth's water. The Atlantic takes the shape of an S when seen from above, bordered by the Americas to the west and by Europe and Africa to the east. It is also the ocean with the lowest volume relative to its area. Its average depth, around 3,300 meters, is shallower than that of the Pacific and Indian Oceans. The Puerto Rico Trench in the Atlantic is the ocean's deepest point, 8,408 meters, and it was where the only fish ever known to be caught below 8,000 meters was retrieved in 1970. A hurricane starts out as a modest atmospheric disturbance over warm ocean waters. For a hurricane to form, temperatures of at least 27 degrees Celsius are needed at a depth of several meters. The highest occurrence of hurricanes is concentrated in tropical oceans, mainly in the North Atlantic. Think of a pot of boiling water. Steam rises, builds pressure, moves air. In the ocean, the process follows similar logic, just on a continental scale. Warm water evaporates. Vapor rises carrying latent heat, Cold air rushes in at the base to fill the vacuum. Earth's rotation imparts spin to the system, and a self-sustaining atmospheric machine begins to take shape. The Atlantic hurricane season runs from June 1st to November 30th, the period during which most tropical cyclones are expected to develop in the North Atlantic. These dates, adopted by convention, cover the stretch of the year when the most cyclone formation occurs in this basin, a 6-month annual window during which the tropical Atlantic becomes a storm incubator. The peak comes in September, when surface waters have absorbed the maximum amount of summer solar heat and upper-level wind patterns favor storm organization rather than tearing systems apart before they gain strength. A hurricane is a tropical cyclone that has become very intense, with winds spinning counterclockwise in the northern hemisphere around a low-pressure center. The lower the pressure at its center, the stronger the surrounding winds will be. They must exceed 119 kilometers per hour to be classified as a hurricane. The Saffir-Simpson scale classifies hurricanes from Category 1 to 5. At Category 5, winds surpass 294 kilometers per hour, capable of stripping entire roofs, knocking down century-old trees, and rendering entire regions uninhabitable for weeks. The pressure at the eye of an intense hurricane is equivalent to the altitude of domestic flights, and that difference relative to the surrounding air is what feeds the violence of the system. The S-shaped Atlantic is no aesthetic accident. It's a direct consequence of the separation of the South American and African tectonic plates, which began about 130 million years ago and continues to this day. The Mid-Atlantic Ridge, which runs through the center of the ocean from north to south, marks the spot where new ocean floor is continuously created from magma rising out of Earth's mantle. This ocean is growing, widening by a few centimeters per year, while the Pacific shrinks by the same amount, consumed by subduction along the edges of the Ring of Fire. The Atlantic is geologically young and still expanding. The shallower average depth compared to the other major oceans, around 3,300 meters versus more than 4,000 in the Pacific, has a direct practical implication. The Atlantic is relatively easier to probe, monitor, and cross with submarine communication cables. The first transatlantic telegraph cables were laid in the 19th century, connecting Europe and the Americas in real time for the first time. Today, dozens of fiber optic cables on the Atlantic floor carry the vast majority of internet traffic between the two continents. Invisible, submerged, transporting billions of messages per second along the bottom of the most navigated ocean in human history. Hurricane winds lose intensity when they make landfall due to the roughness of the terrain and the reduced supply of latent heat. Nearly 90% of hurricane fatalities are caused by drowning. That statistic dismantles the intuition that wind is the main danger. What kills isn't the wind, it's the water. Storm surge, torrential rains, sudden coastal flooding. The water driven inland by the hurricane overwhelms all local drainage capacity, submerging entire regions within hours. The Atlantic, in producing these systems, delivers to the continent not just winds, but tons of ocean water hurled inland. The Puerto Rico Trench, at 8,408 meters deep, represents the deepest point in the Atlantic and one of the least explored places on the planet. Located between the island of Puerto Rico and the North American plate, it results from the subduction of the oceanic plate beneath the Caribbean. The pressure at the bottom exceeds 800 atmospheres. Sunlight has never reached that point. Temperature hovers around 2 degrees Celsius. And yet, species adapted to this extreme environment survive. Transparent fish, crustaceans that have never known the surface, microorganisms with metabolisms built entirely for permanent darkness and cold. Maritime traffic in the Atlantic today is radically different from what it was during centuries of sail navigation, but the essential route remains the same, connecting Europe, the Americas, and Africa. Containers replaced wooden ships. GPS replaced stars as a navigation guide. Crossing times dropped from months to days. But the ocean remains the same, capable of generating Category 5 hurricanes, producing 10-meter waves in winter storms, and swallowing ships that underestimate its conditions. The Atlantic is simultaneously the busiest highway and one of the most unpredictable natural forces on the planet. The major exception to the standard hurricane formation pattern in the Atlantic was Hurricane Katrina, a Category 1 storm that hit the coastlines of the states of Rio Grande do Sul and Santa Catarina in March 2004. An event considered historically impossible, since the South Atlantic rarely presents favorable conditions for hurricanes due to its cooler water temperatures. Katrina rewrote what was known about the geographic limits of Atlantic hurricanes. A statistically improbable event occurred, and it was not a random anomaly, but a signal that the oceanic conditions that prevented hurricanes in the South Atlantic are slowly changing. The Atlantic carries in its very name the memory of the ancient world. It derives from Atlas, the titan of Greek mythology condemned to hold up the sky on his shoulders. And for the ancients, there was something titanic and insurmountable about those waters stretching beyond the western horizon. The ocean that once seemed like the edge of the world became the road connecting continents, the cradle of hurricanes and currents that regulate climates thousands of kilometers away. That same ocean, now monitored by satellites and probes, still holds its depths as territories nearly as unexplored as they were in Magellan's century. The Indian Ocean covers 70 million square kilometers and has a quirk that no other ocean has. Its currents completely change direction every 6 months, driven by monsoon winds. The South Asian monsoon is the largest monsoon system on Earth. The Indian Ocean has the world's greatest meridional heat transport toward the south and is characterized by unusually active intraseasonal variability. The warm waters of the northern Indian Ocean heat the atmosphere above them, creating a low-pressure zone that draws moist air from the ocean toward land. This process is fundamental to the onset and intensity of the summer monsoon. The southwest monsoon winds, from June to October, carry moist air deep into the Indian subcontinent. And when that process fails, it means drought for hundreds of millions of people. The Arabian Sea has the world's thickest oxygen minimum zone. While the Pacific and Atlantic maintain relatively stable current directions throughout the year, the Indian Ocean does something without equivalent in any other ocean. It completely reverses its flow twice a year, as if breathing. The monsoon system occupies the northern portion of the Indian Ocean. Its engine is the seasonal reversal of monsoon winds. In winter, the trade winds blow from the northeast toward the intertropical convergence zone. In summer, the warm, moist winds, drawn in by the low pressures over Asia, cause reheating and partial desalination of the waters, along with an acceleration of currents that flow predominantly eastward. The ocean obeys the continent. When Asia heats up, it pulls sea air into itself, reversing established currents. The monsoon has its origins in the Arabic word mausim, meaning season. Arab sailors used this term for centuries to describe the seasonal shift in wind direction between India and Arabia in the Arabian Sea. The monsoon effect is caused by the seasonal appearance of large thermal differences between the seas and adjacent continental regions. Those sailors didn't need formal meteorology to understand the phenomenon. They just needed to survive. The monsoon was both calendar and compass. It told them when to leave and where to sail. Entire Indian Ocean civilizations built their trade routes around this seasonal oceanic clock. The physical mechanism behind the monsoon is simple in principle, colossal in scale. Land heats and cools more quickly than the ocean. In the northern hemisphere summer, the enormous Asian continental landmass heats up dramatically, creating low pressure over the continent. The ocean, cooler, generates relative high pressure. Air always flows from high to low pressure, and moist ocean air begins blowing toward the Indian subcontinent, carrying the moisture that falls as monsoon rain. For part of the year, the winds blow from the ocean toward the continent, bringing humidity and triggering intense rainfall in countries like India, Bangladesh, Sri Lanka, and Myanmar. In another period, the winds shift direction, making the climate drier across many regions. A weak or delayed monsoon is not just a meteorological inconvenience. It's a potential agricultural catastrophe for hundreds of millions of people. The Indian subcontinent, Bangladesh, and parts of Southeast Asia depend on monsoon rains to fill reservoirs, irrigate rice crops, and replenish groundwater. When the monsoon fails, arriving weak, late, or cut short, the result is a water deficit that affects harvests, drives up food prices, and can trigger humanitarian crises in already vulnerable regions. An ocean with an area equivalent to 7 times the size of Brazil determines, through the temperature of its waters, whether there is food on plates 2,000 kilometers away. Indian Ocean currents are controlled mainly by the monsoon. 2 large circular currents, one in the northern hemisphere flowing clockwise and another south of the equator flowing counterclockwise, make up the dominant pattern. During the winter monsoon, the currents in the north are reversed. This reversal is rare in oceanography. No other ocean shows such a complete and systematic reversal of its surface gyres. The northern Indian Ocean becomes, in terms of current dynamics, a different ocean in summer than in winter. Marine species, nutrient distribution, and even the drift patterns of floating plastic particles follow this calendar imposed by the Asian continent. The Arabian Sea, the northwestern arm of the Indian Ocean, concentrates one of the most extreme characteristics of any ocean: the thickest oxygen minimum zone on the planet. Below a few hundred meters, the concentration of dissolved oxygen drops to levels incompatible with most forms of animal life. This phenomenon results from the combination of high surface productivity, which generates abundant organic matter, with limited deep circulation, insufficient to renew the oxygen consumed by bacterial decomposition. The result is an extensive anoxic water layer, where only anaerobic microorganisms survive, and where chemical processes produce gases such as methane and hydrogen sulfide. The intraseasonal variability of the Indian Ocean, fluctuations that occur within the same season, on timescales of days to weeks, exceeds that of any other ocean. Madden-Julian oscillations, which are pulses of convective activity that travel periodically through the tropics, are more intense and regular over the Indian Ocean than anywhere else. These pulses modulate the intensity of the monsoon within the season itself, generating weeks of intense rainfall followed by dry breaks, in a cadence that farmers have been trying to interpret for generations without adequate forecasting tools. Modern ocean science can track these pulses with satellites, but predicting exactly when they will arrive still challenges the most sophisticated models. The dynamics of Indian Ocean waters are more complex than in other oceans. This complexity has a geographic root. The Indian Ocean is the only ocean closed to the north by a continent, meaning there is no inflow of cold polar water from the north, as occurs in the Atlantic and Pacific. All renewal of its deep waters comes from the south, carried by the Antarctic Circumpolar Current. This northern blockage makes the Indian Ocean warmer, more stratified, and less nutrient-rich at the surface. Characteristics that shape everything from marine biodiversity to the atmospheric patterns of the countries that border it. The southwest monsoon, which blows from June to October, is the most powerful pulse of the system. It carries enough moisture to feed rivers, fill dams, and sustain entire civilizations through the following season. When it reaches the Indian subcontinent, it rises against the Himalayan mountain range and unleashes rainfall of staggering intensity. Cherrapunji, in northeastern India, regularly records some of the highest annual precipitation in the world. more than 11 meters of rain per year in exceptional years, driven directly by this oceanic atmospheric mechanism. An ocean that reverses its currents every 6 months is the reason one of the wettest places on Earth sits in the heart of a subcontinent. The Indian Ocean is the only one of the 5 oceans completely closed to the north, blocked off by Asia. This geographic configuration has direct consequences for water temperature. Its average temperature is warmer due to its northern boundary being largely surrounded by land, which restricts heat exchange with polar regions. This heat contributes to higher rates of evaporation. Salinity varies significantly between the Arabian Sea, very salty, due to high evaporation, and the Bay of Bengal, less salty, due to the discharge of major rivers like the Ganges and the Brahmaputra. The Indian Ocean is home to extensive coral reefs in its tropical sector, the only known populations of certain dugong species, and sailfish, Istiophorus platypterus*, that reach 110 kilometers per hour, the fastest bony fish on the planet. All other major oceans have openings to the north or south that allow water exchange with polar regions. The Pacific communicates with the Arctic through the Bering Strait. The Atlantic exchanges water with both poles. The Indian Ocean extends mostly through the southern hemisphere and is closed to the north by Asia. Largely open to the south and under the influence of the Asian monsoon, it has the shape of a triangle whose median lines are formed by oceanic ridges arranged in an inverted Y. That triangular shape with its apex pointing north, pressed up against the Indian subcontinent, is the key to almost everything that makes the Indian Ocean unique among the world's oceans. North of 20 degrees south latitude, the minimum surface temperature of the Indian Ocean is 22 degrees Celsius, exceeding 28 degrees Celsius to the east. South of 40 degrees south latitude, temperatures drop rapidly. The salinity of surface water ranges from 32 to 37 parts per thousand, with the highest levels occurring in the Arabian Sea. 2 extremes within the same ocean. The Arabian Sea, hypersaline from intense evaporation under tropical sun without enough rainfall to compensate for water loss. The Bay of Bengal, relatively diluted by the massive discharge of rivers like the Ganges and the Brahmaputra, which carry fresh water from the Himalayas to the sea. This salinity difference between 2 arms of the same ocean creates gradients that influence currents, stratification, and the distribution of marine organisms. Indian Ocean waters above 20 degrees Celsius year-round make coral reef formation possible, and the Indian Ocean contains several islands of coral origin. Coral reefs are the tropical rainforests of the ocean. They occupy less than 1% of the ocean floor, but shelter about 25% of all known marine species. In the Indian Ocean, where temperature favors the growth of these calcium-based organisms throughout the year, reef structures reach extraordinary complexity. Some built over millennia, layer by layer, each generation of coral constructing on the skeleton of the one before it. The dugong, an herbivorous marine mammal and distant relative of the elephant, finds its primary global refuge in the Indian Ocean. Endangered marine species in the Indian Ocean include the dugong, seals, sea turtles, and whales. The dugong feeds almost exclusively on seagrass, shallow underwater meadows that depend on warm, clear water to survive. These submarine pastures require specific conditions of temperature, salinity, and light that the Indian Ocean offers across expanses not found in any other ocean. A mammal weighing up to 400 kilograms, moving slowly and grazing on marine plants, is paradoxically an indicator of the health of entire coastal ecosystems. Its presence signals intact meadows, its absence degradation. The sailfish, Istiophorus platypterus, represents the polar opposite in terms of speed within the same ocean that shelters the slow-moving dugong. Sailfish are known for their incredible speed, with streamlined bodies and bills that slice through the water. They are apex predators that hunt in open waters, considered the fastest fish in the ocean. Reaching over 100 kilometers per hour in water, a medium 60 times denser than air, demands extreme adaptations. A fusiform body that minimizes hydrodynamic resistance, a retractable dorsal fin to reduce drag at high speed, and specialized musculature built for short-duration sprints. No bony fish on Earth moves faster. The low biological productivity of Indian Ocean surface waters seems contradictory for a warm ocean. The Indian Ocean stands out for the weak productivity of its surface waters, deprived of revitalizing vertical exchange. Warm water is less dense than cold water, and this density difference prevents surface and deep layers from mixing. The mineral nutrients essential for phytoplankton growth accumulate in the cold depths. Where light doesn't reach, the sunlit surface is left nutrient poor. The result is warm, blue water, beautiful, transparent, biologically sparse. The exceptions occur in coastal zones where the monsoon triggers upwelling of cold, nutrient-rich water, generating intense seasonal blooms of marine life. The Indian Ocean contains 16% of the world's coral reefs. Global warming has been causing a steady rise in annual maximum temperatures, which is killing corals near the ocean's surface at an alarming rate. Corals live in symbiosis with photosynthetic algae called zooxanthellae, which reside in the animal's tissues and provide up to 90% of its energy. When water temperature rises just 1 or 2 degrees above what is tolerated, the coral expels the algae, a process known as bleaching, and turns white, fragile, and vulnerable to death. The Indian Ocean, already the warmest of the major oceans, has a narrower thermal safety margin than the others. Small temperature variations have disproportionate consequences in an environment already operating at its limit. The ocean closed to the north that warms the most, evaporation that raises its salinity, currents that reverse with the seasons, reefs that sustain immense biodiversity, dugongs that graze slowly in submarine meadows, and fish that reach highway speeds. All of this coexists in the same triangular body of water that Arab sailors simply called home. The Indian Ocean was the first ocean in history to be systematically navigated by humans, and it still holds, in its depths and in its seasonal rhythms, secrets that modern ocean science continues patiently to decipher. The Arctic Ocean covers 14 million square kilometers, smaller than the surface area of Russia, and has an average depth of just 1,038 meters, the shallowest of the 5. Summer sea ice has shrunk by more than 40% since 1979. The Arctic is warming 2 to 4 times faster than the global average. The mechanism driving this accelerated warming is physical. White ice reflects sunlight back into space, while the dark ocean below absorbs heat. Every piece of ice that melts exposes a surface that absorbs even more heat, which melts more ice, a self-feeding cycle. An estimated 22% of the world's yet-to-be-discovered oil and gas reserves lie beneath the Arctic. That same ocean floor contains layers of submarine permafrost that, as they thaw, release methane, a gas with 84 times the warming power of CO2 in the first 20 years after emission. Starting with size helps calibrate the scale. 14 million square kilometers is roughly the area of the African continent. Of that total, a substantial portion is water permanently covered by ice, or at least it was until recent decades. An average depth of 1,038 meters sounds impressive until you compare it to the more than 4,000 meters of the Pacific. The Arctic is proportionally like a shallow basin sitting on top of the world. That shallowness has a direct consequence. Shallow water heats up more quickly than deep water, since there's less volume to distribute the absorbed heat. The Arctic's accelerated warming mechanism has a technical name: ice albedo feedback. Albedo is the fraction of sunlight that a surface reflects back into space. The loss of sea ice not only increases warming in the Arctic, but also contributes to rising global temperatures through ice albedo feedback. Ice and snow have very high albedo. They reflect up to 90% of incoming sunlight. Dark ocean has very low albedo. It absorbs up to 94% of that same light. Replacing ice with ocean is like swapping a mirror for a heat sponge. The result is amplification. The more ice that melts, the more heat is absorbed, which melts even more ice. In the Arctic, the main methane sources influenced by this process include permafrost thaw, Arctic sea ice melt, and the destabilization of clathrates. Methane release results in a positive climate feedback, a process that amplifies global warming, since methane is an extremely potent greenhouse gas. Clathrates are crystalline ice structures that trap methane molecules inside them. As long as they stay cold and under pressure, these ice cages keep the methane locked in. When temperatures rise or pressure drops, the cages break apart and the methane escapes into the water and then into the atmosphere, where it warms the planet, which melts more clathrates. Permafrost, permanently frozen ground, stores large amounts of carbon in the form of organic matter that became trapped in ice over thousands of years. When it begins to thaw due to rising global temperatures, that carbon is released in the form of carbon dioxide and methane, two potent greenhouse gases. This gas release process can accelerate global warming, creating a vicious cycle. The carbon accumulated in permafrost represents centuries of organic material, leaves, roots, animals, that never decomposed because it remained permanently frozen. Thawing works like opening an old freezer packed with organic matter. Decomposition begins immediately, releasing gases that have been stored for millennia. The most dangerous feedback is the release of methane from the Arctic Ocean seafloor, as hydrates are destabilized when heat reaches the sediments. Elevated air temperatures cause the warming of river water flowing into the Arctic Ocean, resulting in further sea ice decline and warming from the surface all the way down to the ocean floor. Siberian rivers carry water warmed by the continental interior into the coastal Arctic. Fresh, lukewarm water that seeps beneath the sea ice, heating the bottom from below while the atmosphere heats from above. The pressure comes from two directions at once. Several countries have billions of dollars worth of infrastructure in the Arctic that is at risk of collapse as the underlying permafrost thaws. Indigenous Arctic peoples have maintained a long relationship with their frozen environment and now face the loss of their cultural heritage. Roads built on permafrost that was assumed to be permanent are sinking. Buildings erected on that ground are cracking. Coastal cemeteries are being swallowed by the encroaching sea, where coastal ice once served as a barrier. The faster-warming Arctic is not just an abstract climate problem. It's the physical and cultural loss of territory for populations that have called this region home for generations. A third of the volume of Arctic winter sea ice has been lost in just 18 years. The oldest frozen layers tend to be the thickest and most resistant to melting, and those are exactly the layers disappearing first. Multi-year sea ice, formed by layers built up over decades, is thicker, more resistant, and survives more summers than seasonal ice formed in a single winter. As the old ice disappears, it's replaced by thinner seasonal ice that melts more easily the following season. The Arctic is losing its cold memory. The opening of new Arctic shipping routes, such as the Northwest Passage and the Northern Sea Route, is often presented as an economic benefit of the ice melt. Cargo ships save thousands of kilometers compared to routes through the Suez Canal or the Panama Canal. What rarely makes it into that calculation is the systemic cost. Every ship that sails through the Arctic releases black carbon, soot, that lands on the ice and reduces its albedo even further, accelerating the melt. The logistical benefit and the climate cost occur in the same ocean, in almost the same act. The transformations currently underway in the Arctic are expected to be irreversible for centuries or even millennia. Some sea ice does reform each winter in the Arctic, but ice-free summer events are expected to occur with increasing frequency as warming intensifies. An ice-free Arctic in summer doesn't mean an ice-free ocean year-round, but it does mean the polar thermostat that regulates the climate of the entire northern hemisphere would be operating under conditions radically different from anything humanity has known since it began keeping weather records. The smallest and shallowest of the 5 oceans carries, paradoxically, one of the greatest climate responsibilities on the planet. The 5th ocean is the only one whose boundaries are not continental coastlines. They are drawn by a water current. The Southern Ocean is unique in being defined by a current, not by land, and plays a vital role in the global climate. The Antarctic Circumpolar Current, which marks the boundary of this ocean, is the largest current on the planet. It is the only current in the global ocean that closes in on itself in a circumpolar loop. That trait makes it the most important current in Earth's climate system because it links the Atlantic, Pacific, and Indian Oceans, serving as the primary means of exchange between basins of heat, carbon dioxide, chemical substances, biological life, and other tracers. The Antarctic Circumpolar Current transports 100 times more water than all the rivers in the world combined. The Southern Ocean absorbs more CO2 from the atmosphere than any other ocean, functioning as the planet's largest net carbon sink. An ocean defined by a current, not by a coastline, is a concept without parallel in all of geography. Every other ocean is demarcated where water meets land. The Atlantic ends on European and American beaches, the Pacific on Asian and American shores, the Indian at the southern edge of Asia. The Southern Ocean ends where the temperature and density of the water change, where the Antarctic Circumpolar Current creates a physical boundary that is invisible but measurable, detectable by instruments, and sensed by marine organisms that rarely cross it. It is the Southern Ocean that defines its sister continent, encircling it completely, the reverse of the usual logic in which continents define oceans. The Antarctic Circumpolar Current transports more than 100 times the total water volume of all the world's rivers combined and continuously circulates around Antarctica without being interrupted by any continent. Because of this unique characteristic, it exerts enormous influence over the global climate and Earth's ocean circulation. To grasp that scale, the Amazon, the world's largest river by volume, transports roughly 209,000 cubic meters of water per second. The Antarctic Circumpolar Current carries more than 100 times the combined flow of all the world's rivers. It is not just a current, it is an ocean in permanent rotational motion. The Antarctic Circumpolar Current connects the Atlantic, Pacific, and Indian Oceans, flowing eastward in the southern hemisphere and encircling Antarctica. The Southern Ocean plays a fundamental role in Earth's climate, absorbing a fraction of the carbon dioxide produced by human activities and helping to balance the buildup of that gas in the atmosphere. Picture the current as a circular corridor through which the other 3 oceans connect. None of them would communicate directly with the others without this southern ring passage. Water, heat, salt, carbon, and nutrients that enter at any point in that corridor end up distributed among the 3 oceans over the course of decades. The Southern Ocean absorbs a massive 2 billion tons of CO2 over the course of a year. In summer, the proliferation of photosynthetic algae, phytoplankton, contributes to this absorption. 2 billion tons is a quantity that defies intuition. It's equivalent to the weight of more than 200,000 Eiffel Towers being pulled from the atmosphere annually and deposited on the ocean floor. That carbon doesn't simply vanish. It dissolves in the cold water, is consumed by organisms, and sinks with them when they die, remaining sequestered in the depths for decades or centuries. Researchers discovered that the Southern Ocean's capacity to absorb CO2 is 25% greater than previous estimates suggested. Direct air-sea measurements indicate that earlier models underestimated CO2 absorption. The upward revision of the Southern Ocean's capacity as a carbon sink is relatively good news. The ocean is doing more climate work than previously thought. The question that remains open is whether that capacity will hold up as surface waters warm, since warmer water reduces CO2 solubility. A warmer ocean absorbs less gas, and the Southern Ocean is also warming. The Antarctic Circumpolar Current acts as a natural barrier against invasive species, such as groups of seaweed or shrimp and mollusks arriving from other continents. Under a high-emissions scenario, the Antarctic Circumpolar Current is expected to slow down by about 20% by 2050. This biological barrier has kept Antarctic ecosystems isolated for millions of years, allowing the evolution of unique species adapted to extreme cold. A weaker current is a more permeable boundary, and species from other oceans, favored by warmer waters, could cross into an environment where no natural predators or competitors have ever existed to keep them in check. The Southern Ocean allows surface and deep waters to flow freely from west to east around Antarctica, making it critically important for linking the three oceans: Atlantic, Indian, and Pacific. At the surface, there is the Antarctic Circumpolar Current. In the deep ocean, there is the circulation of Atlantic water masses toward the Indian and Pacific, two simultaneous and opposing levels of circulation. At the surface, the circumpolar current moves water eastward. In the depths, cold, dense water masses from the North Atlantic, which sank after releasing their heat, travel slowly southward and are redistributed to the other oceans through the Antarctic corridor. The lower level is the ocean's memory of what happened on the upper level centuries ago. New research has reconstructed how the Antarctic Circumpolar Current emerged roughly 34 million years ago. The new circulation helped the oceans absorb more carbon dioxide from the atmosphere, contributing to a global cooling that ultimately triggered what is known as the Cenozoic Ice Age, which still influences the planet's climate today. This current is not static. It arose in response to the tectonic plate movement that separated Antarctica from the other continents. When Australia drifted far enough from Antarctica, westerly winds gained an unobstructed path around the South Pole, and the current became established. That geological event from 34 million years ago changed the global climate, and the current that emerged then still regulates the planet today. The Southern Ocean is the newest of the five in terms of formal recognition, the most remote in terms of human access, and the most fundamental in terms of global climate function. If the circumpolar current breaks down, severe consequences are expected, including greater climate variability with more extreme events in certain regions and accelerated global warming due to the ocean's reduced capacity to act as a carbon sink. The current that no coastline defines, marked only by the physics of water in motion, silently sustains the climate system that allows all the other oceans to function as they do, and that allows life along the shores of every continent to organize itself around patterns that human beings take for granted. The Pacific covers 165 million square kilometers and holds the deepest point on Earth. The Atlantic maintains the current that warms Europe and generates hurricanes. The Indian Ocean has its winds reversed twice a year and the thickest oxygen minimum zone on the planet. The Arctic loses 12.2% of its summer ice per decade and warms 2 to 4 times faster than the rest of the planet. The Southern Ocean, defined not by coastlines but by a current, absorbs the carbon that the rest of the atmosphere accumulates. Although they are all interconnected, these 5 oceans were divided based on historical, geographic, and cultural factors. The heat that El Niño generates in the Pacific shifts into the Atlantic through the AMOC, which deposits cold water in the depths of the South Atlantic, which connects to the Southern Ocean via the circumpolar current, which distributes that same heat and carbon around the entire planet and back to the Pacific. 5 names, 1 circulation, 1 system. Beyond the movement of water masses, thermohaline circulation transports heat, salt, oxygen, carbon dioxide, nutrients, and other properties from higher to lower latitudes throughout the global ocean, setting off a chain of consequences. That technical sentence deserves a concrete translation. The water that cooled in the Arctic and sank in the North Atlantic carries dissolved oxygen down into the depths of the Indian Ocean. Nutrients absorbed by organisms in the Pacific sink with the bodies of those organisms, are carried by deep currents, and eventually resurface in another ocean, thousands of kilometers and decades later. The oceans continuously exchange their properties, a permanent loan between basins. The oceans store 50 times more carbon than the air. 1 kilogram of water stores 4,000 times more heat than 1 kilogram of air. Just 2.5 meters of ocean stores as much heat as the entire atmosphere. This contrast in capacity explains why the oceans are so decisive for climate. The atmosphere is thin, light, and changes temperature quickly. The ocean is dense, heavy, and changes slowly. When the planet accumulates extra heat from any source, more than 90% of that excess goes into the ocean. The ocean is the planet's primary thermal buffer, the reason atmospheric warming occurs more slowly than it would in a world without seas. The water that descends in the North Atlantic enters the Antarctic Circumpolar Current, and from there enters all the other ocean basins, where it slowly rises into the upper kilometer and returns to the North Atlantic. This pathway functions as the primary sequestration route for atmospheric greenhouse gases. That circuit takes about 1,000 years to complete. Water that sinks today in the North Atlantic will emerge in some part of the Pacific or Indian Ocean around the year 3000. The carbon it carries will remain out of the atmosphere for all that time. Not destroyed, just stored in the cold depths, far from the surface where it would interact with the climate. The loop connecting the 5 oceans is not a theoretical abstraction. It is a physical process measurable by satellites, ocean buoys, and deep-sea probes. Ocean circulation doesn't just distribute heat. The oceans also absorb carbon dioxide from the atmosphere, acting as a massive carbon sink. Ocean circulation carries that CO2 into the depths, where it can be stored for long periods. This process is essential for moderating atmospheric CO2 levels, and by extension, climate change. Without this active sequestration by the oceans, atmospheric CO2 concentration would be substantially higher than it is today. The ocean is not just the backdrop for climate change. It is one of the main forces slowing it down. The connections between the 5 oceans reveal why no ocean crisis is local. Global warming can trigger cooling in the North Atlantic, Europe, and North America through the weakening of thermohaline circulation, and can also cause shifts in tropical rainfall patterns, more frequent and intense El Niño events, and reduced oxygen levels in the ocean depths. An event in the equatorial Pacific reshuffles the Indian Ocean monsoons. Arctic melt dilutes the North Atlantic and weakens the AMOC. A weakened AMOC alters the flow of cold water that feeds the Southern Ocean. A disrupted Southern Ocean redistributes heat and carbon back into the Pacific. Everything is connected, and the points of vulnerability in one ocean are also the points of vulnerability in all the others. Ocean biodiversity follows the same logic of interconnection. Fish larvae, algae spores, invertebrate eggs, countless marine organisms ride the currents like involuntary passengers, colonizing new territories, transferring genes between populations separated by thousands of kilometers. Changes in water circulation equally impact ocean chemistry and the organisms that live in it. The ocean distributes and absorbs heat in order to regulate climate across different timescales. Altering the currents isn't just a climate problem. It's a reorganization of the dispersal routes for global marine life. with consequences for ecosystems that took millions of years to reach their current balance. Geographers created 5 names to make communication and study easier. Physicists and oceanographers work with a single system. Both are right within their own purposes. The name Pacific Ocean lets a sailor know where they are. The concept of global thermohaline circulation lets a climate scientist understand why the temperature in Oslo depends on what happens at the equator. Technically, the planet has just one enormous ocean, and since it's necessary to locate different parts of that same ocean in distinct places around the globe, it became necessary to define boundaries between those sections. The 5 names are humanity's solution for communicating about one single thing that is too vast to be treated as one single thing. The single ocean covering 71% of the planet was born from comet and asteroid impacts in Earth's first billion years, grew while life was still single-celled, and will remain long after any current human structure has dissolved. In that context, the division into 5 is a recent convention, and the recognition of the 5th ocean in 2021 is a reminder that even systems as fundamental as the oceans continue to be rediscovered and redefined as human knowledge advances. The surface and deep circulation systems in the global ocean are directly interlinked, forming thermohaline circulation. Surface water currents generated at low latitudes travel toward high-latitude regions, where they cool down, increase in density, and sink vertically toward the deep ocean. The water that splashes against the rocks on any random beach has already made that complete circuit, and will make it again, regardless of whatever name any map assigns to it. The same ocean that Magellan crossed in 1521 without understanding what kept him warm. That Arab sailors navigated by the Indian Ocean monsoons without knowing the physics behind them. That Peruvian fisherman called El Niño without imagining that its currents were dictating harvests in Brazil. That single ocean, divided into 5 by human convention, is the most complex and most fundamental system that humanity inhabits without ever having fully understood it. Every name given to it reveals as much about the limitations of the human gaze as it does about the thing it was trying to name. A single system covering nearly 3/4 of the planet, moving heat, carbon, and life through every corner of itself, and beginning where it ends, exactly like the story that described it.